Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on electricity markets. So the learning objective for this lesson is to solve some simple examples of electricity market clearing problems to gain intuition of locational marginal price. Just to give you examples to appreciate the power of optimization in this important aspect of modern society. Let's go through again or look at this LP models for market clearing again quickly. So we have a maximization of total social welfare, which include a special case of minimize generation cost. We have flow balance constraints and other physical constraints in terms of flow limit, generation limit, demand limit. The important thing is at each node in the system, we'll have the so-called locational marginal price, pi i's, pi 1, pi 2, pi 3, pi 4. These are electricity price at that location. And the meaning of these price is important. The meaning is a marginal cost of serving one more unit of electricity at the current situation. So when you solve this problem, the market clearing problem, demand and supply will be fixed. And then you can ask the question, if I increase the demand just a little bit, then how much more generation I need and how much more cost will appear. So that is the marginal price. Let's see some simple example. Here is probably one of the simplest example that we can consider. Is a network of only 2 nodes and connected by one transmission line or one edge. We have 2 generators, generator 1 at node 1 and generator 2 at node 2. We have 2 loads, each at a node. So here are some data. So the generator companies bid into the market. So for example, generator 1 offers at $20 to sell per unit of electricity. In this case, we call it megawatt hour. This is a usual unit in wholesale electricity market. It's a pretty big quantity of amount of electricity, can serve thousands of households. But for this electricity market on the wholesale level, they measure electricity in this unit of 1 megawatt hour. So generator 1 offers $20 per unit with a capacity of 150 units or megawatts. So generator 1 can supply up to 150 units at this price. And generator 2 is another company operating at node 2, offers $10. It's a lower price, and the capacity of this generator is actually higher, 300. The difference can come, for example, from different fuels that generators burn, and different types of generators can determine different capacities. This kind of situation happens all the time in electricity market. And the demand, in this case, are fixed. For example, demand 1 is fixed at 150 megawatt or 150 units, and demand 2 is fixed at 100 units. Okay? The problem is, how do we clear the market by matching supply and demand, and how do we decide electricity price? So we need to specify one more piece of information, and this information is the transmission capacity, how much power I can send through this transmission line. In this case, which is case 1, we specify a pretty high number, 300 units. On this transmission line. So this is a high capacity transmission line. And we'll see that this transmission line has so much capacity so that the system actually has no congestion, meaning there's no problem sending power between 1 and 2 through this line. And since the transmission line capacity is so high, if you look at the numbers, 300 actually is more than the sum of the total demand, which is 250. That means no matter how much, what is the solution, how much power is sent through to satisfy demand, the constraint here, especially the amount of power transmitted on the line 1, 2 can never reach the upper or lower limit, right? At most it's 250, but the capacity is 300. This big F12 is 300. So this constraint is never binding or never active or never active, or the inequality never becomes equality. So this situation is called no congestion. There's no congestion, just like traffic. There's no congestion or no traffic jam on the transmission line. So we can ignore the transmission flow constraint, and then the problem actually becomes very simple. We don't even need to use a solver. We want to minimize the total cost to satisfy demand in this case, because demand is fixed. So we look at, we have 150 capacity at $20, 300 at $10. So we use the lower cost first to satisfy as much demand we want. For example, we have 300 capacity at $10 for generation, and we only have 250 unit of demand. So that gives us a simple problem. So the minimum cost generation will be from generator 2, which supplies all the demand, 250 megawatts. And generator 1, because it's more expensive, it's actually not needed in this case. And the amount of power flowing from 2 to 1 is exactly 150 unit to satisfy demand 1. So generator 2 generates 250, 100 goes to this load, and 150 goes to this load. So then the question is, what is the electricity price? Again, the intuition is important. The electricity price is the cost of increasing the amount of demand by a little bit. How much cost increase? So here we look at what is the price at node 1. If I increase the demand here by a tiny unit, then what is the rate of increase of the cost? Well, if you increase demand by a little bit, then this generator, this cheap generator, will keep supplying this demand. Well, that cost of supplying that actual demand is at $10. So the electricity price at node 1 will be $10. And so it's for node 2. If the demand here is increased by a tiny bit, then that demand will be again supplied by the cheaper unit or cheaper generators here at $10 because the generator has enough capacity to supply that. So the electricity price at node 2 is also going to be $10. And the important thing here is for node 1, why can we supply node 1's load from node 2's generator? That's because the transmission line here is not congested. You still have capacity to supply the extra delta amount of electricity load here. So that's why for the no congestion case, the electricity price at node 1 equals to the electricity price at node 2. This is called uniform price. So the electricity price is the same across the network. That's what we said. There's no congestion, the price is uniform. Okay, let's look at another case of this simple example. Same system with 2 nodes, 2 generators, 2 demand. Generator, same bidding, same capacity, demand at same level. The only difference is, in this case, transmission capacity, amount of power that we can transmit along this edge, is only 80 units or 80 megawatts. So this is much lower than 300 in the case 1. So because this is only 80, the transmission constraints will be binding, meaning we'll use up all the transmission capacity here from 2 to 1. So we cannot ignore the transmission constraint, and the market clearing problem will give this solution, which we can also look at the graph and data and figure out. So because generator 2 here is again the cheaper generator, we'll use it as much as possible to supply all the load here, 100 units. And then we still have actual capacity, so we're going to start supplying load at node 1. But because the transmission capacity is limited at 80, so we can only supply up to 80 units to load 1. but load 1 is 150. So that's why we need to pick up from generator 1, 70. So that's why P1, generator 1's output is at 70 units, and generator 2's output is at 180 units. And the amount of power transmitted through this line is negative 80 because the convention of direction is from 1 to 2, being positive. The real flow is from 2 to 1, so that's why it's negative 80. So what is marginal price? Well, the price, let's look at for load 2 first. Well, load 2, if we increase load 2's demand a little bit, because of the generator 2 still have more capacity to offer, so we'll use that. We'll use generator 2 to satisfy the actual demand at load 2 at price 10. So that's why the locational marginal price at node 2 is $10. Okay. Well, node 1. Well, at node 1, if node 1's load increase from the level of 150 and increase a little bit, then because this transmission line is congested, we cannot deliver cheap energy from 2 to 1 anymore. We have to use the more expensive generator 1 here at cost of 20. So that's why the locational marginal price of load 1 at this location is actually $20 per unit of energy. So that is a higher price. Okay? And this example actually shows the intuition, the important observation that when there is transmission congestion, when the system is limited in how the flow can be transmitted, then there will be a differentiation of price in different locations because cheaper energy cannot be supplied to the demand center where the demand is as freely as possible. So that creates a shortage of supply in the demand center where the demand is, and that shortage has to be picked up by generator nearby, which usually are more expensive generators. So this phenomenon happens in the real world, and the reason is exactly this. So let's see some real world example here. We'll see actually the locational marginal price distribution in 4 different markets in the United States. The ISO New England in the Northeast, 6 states, PJM market, Pennsylvania, New Jersey, Maryland, also part of Virginia, and New York ISO market only serves New York State, and in fact only serves almost all the demand of New York ISO comes from New York City and Long Island. And Mid-Continental ISO, this is a huge ISO. Let's look at their price distribution. So there are a lot of information here on their website. This is a website of ISO New England, and you can see their real-time price map right here. This is the footprint of the system with 6 states here, Maine, New Hampshire, Vermont, Massachusetts right here. The dot here is where the system operator is. ISO New England locates in the middle of Massachusetts. Okay, and if you click on here, you can see that locational marginal price LMP is $13.37, which actually is a very cheap price right now. You see there's differences. For example, here in Connecticut, close to New York, you can see that the price is slightly higher, $13.62. In other area, for example, New Hampshire and Maine, which actually is bordered with Canada, Quebec, hydropower is very cheap power. You can see that their price is also lower. So this situation is, although it has a little bit price difference, still pretty uniform. Let's look at some other system. For example, PJM is a huge ISO. We see their footprint is much bigger than ISO New England. You can see there they cover Chicago here, Philadelphia, Pittsburgh, several big cities. You can also look at their marginal price at different locations. All these numbers are different locations, $22 to $19. These are the difference exactly created by transmission line congestion, so that cheaper generation electricity cannot be transmitted to load centers. There is a limit that creates a price differential. If you look at ISO New York, you'll see another footprint here. ISO New York operates state of New York, and you can see that New York City is right here, price $30.77, more than twice price in New England, which is just next door. And Long Island is also very high price, and this price changes every few minutes. If you are upstate New York, you can see that price is, for example, here $14, more than half of the price in New York City. That's created by the load, because New York has a lot of load, and the power transmission going to the city is limited. So the generators in the city is more expensive. That's why the price in New York is higher. Mid-continental ISO, similar. That we'll see that it's a large ISO with a huge footprint. The colors here are the LMP value. Again, right now is in the morning. System is not very highly loaded. In the afternoon, when there's a peak demand, you can see that the price differential is much higher, will be much higher. All right, let's summarize. So we have looked at how to compute locational marginal price. We explored the intuition of location marginal price by a simple two-node system. The intuition is very important, and it applies to real-world system. And we examined some real-world electricity market and look at their real-time pricing distribution. So to summarize, we see that these LP models and location marginal price dual variables are actually used every day, every few minutes in this country to clear the electricity markets across the continent. So we'll see that optimization and the meaning of optimization actually is very important in our real modern society. So this is the end of our discussion on electricity market. Thank you.